In this video, we'll explain the uncertainties associated with measurements in different circumstances that you may encounter in the lab.
Our first example will be a simple measurement of the radius of a smooth steel ball.
Say we want to measure the radius of a small steel ball. We have two different instruments we could choose to accomplish this: a vernier caliper or a ruler, shown here. Measuring with the ruler is inherently difficult because of the shape of the ball, which can result in parallax error and basically makes the measurement difficult. The vernier caliper, on the other hand, is well adapted to measuring the external dimension of an object, provided that it doesn't exceed the dimensions of the jaws of the caliper. Therefore, we will choose the vernier caliper as the optimal measuring device for this measurement.
Ensure that you include titles and the reading error of your measuring device in your datasheet. Since we chose the vernier caliper, we have an extra digit of precision, and our reading error is 0.05 millimeters. The saying, "measure thrice, cut once," applies equally here, and it is also advisable to share measurements amongst lab partners to avoid bias in measurements. For this case, there is very low variance in the measurements, so we stopped after 4 trials.
Once you have your measurements, you can perform calculations at home using Excel. We want to measure the average diameter and the corresponding standard error. You can use the average button from the auto sum menu or manually type the formulas as appropriate. When calculating standard error, a useful trick is to use the count function and enter a cell range. That way, if you later change the number of cells, the standard error will properly auto-update. We observed a low variance in our measurement, which is supported by the low calculated standard deviation. Therefore, the standard error will always be smaller than the reading error, so we will use the reading error as a measurement uncertainty in this case. This yields a final measurement of the diameter of 19.04 plus or minus 0.05 millimeter, which in turn gives our desired measurement of the radius of a steel ball to be 9.52 plus or minus 0.03 millimeters, noting that the final error was propagated.
Our next example will be a more difficult measurement of the radius of an irregular object.
Based on our previous experience, we will choose the vernier caliper to make our measurement. We can see that there's a high variance in the diameter of this object, therefore we will take many measurements from many angles in order to achieve the highest confidence in our average.
We've prepared our Excel file from our measurement data in such a way that the average value, standard deviation, and standard error will update as the values are entered. You will notice that the standard deviation fluctuates around a constant value. However, the standard error decreases as more measurements are entered. Practically speaking, in the lab, most high variance measurements will involve a moving object. Once every trial has been entered, we can see that the standard error is much greater than the reading error of the device. Therefore, in this case, we will choose the standard error as a measurement uncertainty on the diameter of the irregular object.
This yields a final measurement of 17.2 plus or minus 0.9 millimeters for the average diameter and 8.6 plus or minus 0.5 millimeters for the average radius of the irregular object, again noting that the standard error was propagated for the final error on the radius. In this example, we will investigate some of the issues when measuring the length of an object that exceeds the dimensions of the vernier caliper.
To measure the length of the spring, it is usually most convenient to align one end with the 0 mark on the ruler, and then to measure the position of the other end. We will repeat this measurement only a few times because there is low variance in the measurement. Here is a sample of what your datasheet would look like. Note that the reading error on the position measurements is half the smallest division of the ruler, which is 0.5 millimeters. However, since the length is calculated from 2 end positions, we need to propagate to find the final error on the length. Therefore, since this case has a low standard error, we propagate the reading error to determine the final measurement uncertainty on the length of the spring, which is 0.7 millimeters.
In the previous example, there were few measurement uncertainties. However, in the lab, you may encounter cases where the measurement is difficult and susceptible to parallax error or the apparatus is unstable. When this happens in the lab, it is up to the experimenters to ensure that they perform their measurement with the least error possible, and if necessary, to estimate a larger uncertainty that represents the true error in the measurement.